Hello, and welcome to the video accompanying Chapter 5 on the topic of terrestrial worlds. This is the first of two videos for Chapter 5. In this first video, I'm going to talk about a lot of ideas about planetary atmospheres and planetary surfaces, really getting into, in the interiors to some extent, some general ideas. From everything from earthquakes to the upper atmosphere to understanding weather and how these ideas would generally apply to any planet like Earth that has a rocky surface, a solid core, and potentially an atmosphere, or at least the potential to have an atmosphere. Okay, so this wouldn't apply to the Jovian worlds, the gas giants, the ice giants. Okay, so that's going to be the first half of the slides basically, and this first video. In the second video, I'm going to talk about some specifics about the terrestrial worlds in our solar system. So I'm going to go into some specific details about Mercury, some specific details about Venus, about Earth, about the Moon, which isn't a planet, but it's close to us and special to us, and about Mars. Okay? So that's going to be the dividing line between the two videos, splitting up the lecture in two halves. Well, let's get to it. We have a lot to talk about. All right. So let's first start with planetary geology, Earth and the other terrestrial worlds. All right? Our goals here are to learn what are terrestrial planets like on the inside, what causes geological activity, and why do some planetary interiors create magnetic fields. Okay? So here we have the five main topics that we'll be talking about: Mercury, Venus, Earth, Earth's moon, and Mars. And again, in the second video, I'm going to get into more details about these worlds and the one moon. Okay? And we have some surface pictures, quite fascinating, showing the different surfaces of the planet. Obviously, Earth is the only one that has water and foliation, plants. Okay, so quick idea here: earthquakes, called seismic waves. All right. Well, there's different types, and they behave differently depending on the features of the planet. So the liquid outer core bends P waves, okay, but it stops S waves. So vibrations that travel through Earth's interior tells us what Earth is like on the inside. Because, check this out, the P waves get bent, all right? They come in and they take this bending path shown here. This S wave, which is shown as this wiggly line, just dead ends. So that means that depending on how earthquakes will travel from one point on the surface to another point on the surface, or even a third measured point on the surface, tells us about the interior. So we can actually map out the interior features of the Earth and realize that from here to here, the Earth must be liquid based on the type of waves and how they travel through the Earth's interior. And we could theoretically do this on other worlds as well. Okay? And this tells us that the core of the planet, starting from the inside out, is very dense, made of nickel and iron. It is essentially solid, superheated, highly pressurized. But the outside of the core is liquid. Okay? Past the core is something called the mantle. It is moderate density, has a lot of silicon, oxygen, and other elements. The crust is the lowest density by far. This is the rocky crust, made of granite, basalt, and so on. All right? It floats on top of the mantle. Okay? So how does the terrestrial interior compare to other planets? Again, more details in the second video. I will stop saying that. Okay? Well, we can see, Earth has a relatively large metal core. Venus is really quite similar. Okay? And this is just based on some models, basically kind of how the planets behave, their mass and density and so on. Also something called their rotational inertia. Mars has a much smaller core. Mercury has a huge core. It's mostly core. And the moon would have a very small core, even smaller relative to its overall size. Okay? So this is applying what we've learned about the interior of our planet to other planets. All right? So how do we end up with this idea of having a dense core and a less dense surface? Well, it has to do with something called differentiation. So gravity pulls the high density material to the center. The low density material rises to the surface. This is what would happen in a bucket of water, right? The sand settles to the bottom because it's denser than the water. The lower density water rises up to the surface. The material ends up separated by density. Okay, so planets have differentiation. The densest material sinks to the bottom. If you recall in the last video when we talked about the formation of the solar system, I made a point of saying that doesn't apply to solar systems. It's the reason that we have the dense planet Mercury near the sun isn't because the Mercury sunk towards the sun, because it's very different dynamics, okay, for planets in orbit. But for the actual planets, it is true. The denser material actually sinks towards the center, driven by gravity. Okay? So the lithosphere, well, that's the planet's outer layer of cool, right? Not liquid, not like molten, rigid rock, and it's called the lithosphere. It floats on the warmer, soft rock that lies beneath. Okay? The mantle is partially liquid. Okay? It's kind of like viscous, right? It's very slow moving, like kind of half melted. Okay? But the lithosphere is solid. Okay? So how can we even think about maybe rock in that half liquid state? Well, we can actually think about silly putty as a good analogy. So rock stretches when pulled slowly, but breaks when pulled rapidly. The gravity of a large world pulls slowly on its rocky content, shaping the world into a sphere. And so the rock can remain relatively solid, but behave kind of in a stretchy liquid way. Just like if you pull silly putty slowly. If you haven't done this, I highly recommend it. But if you pull it quickly, it snaps. Okay? That's the same for rock. All right? So how do we know about the Earth's interior? I said it's that we can kind of get this information by considering these different types of earthquake waves that travel, and how S waves don't travel through the liquid part of the outer core, but P waves do. Well, here's a quick explanation of those two different types of waves. So P waves push matter back and forth. They're like a slinky where if you push on it, then you send this type of wave that is kind of regions of denser slinky and regions of less dense slinky. And those regions of density essentially travel, they transmit down the slinky. P wave really stands for like a pressure wave, okay? An S wave, on the other hand, is where you wave the slinky up and down. And this would work with a string as well. Here the wave actually travels as basically a movement, a deformation away from a baseline, right? Which would be the slinky at rest. So here, the change is in the vertical direction rather than the change in density. Okay? So one pushes matter back and forth, and the other shakes matter side to side. Okay? So P waves do go through the Earth's core. They're able to travel through liquids. All right? And that's true. P waves travel through liquid. We have them travel. Sound is a P wave. You can transmit sound through the ocean. You can also transmit earthquake P waves through the ocean, and of course the liquid outer core of our own interior planet. But S waves, like the wave on a stringed instrument or the slinky picture here, they don't transmit through liquids. You can't put an S wave through a liquid, okay? Because the liquid would just disperse. You can't shake the liquid from side to side. That's not the way liquids work, okay? So that means that S waves cannot travel through the liquid, and we can conclude that the Earth's outer core must be a liquid, okay? So what is necessary for differentiation to occur on a planet? Make sure you can answer this question based on the slides we just talked about. Take a moment. Okay, it's B and C. It must be a mix of materials to begin with. You can't just have one uniform density. And the material inside must be able to flow, okay? And the rock is able to flow slowly over time, driven by gravity, okay? So what causes geological activity, right? How do we have things like moving plates in our case, or even volcanoes and rifts and lava flows and so on? What makes that possible? Well, the heating of the planetary interiors is a key part of that puzzle. Accretion and differentiation when planets were young. So if you remember, accretion was a term that we talked about in the last chapter. Accretion was the idea how planets are formed in the first place by rings of dust. So those rings of dust eventually conglomerate together into one larger dust ball. That dust ball is so big it starts picking up more dust balls, eventually becoming a planetoid, and when it becomes even bigger, a planet, clearing out all the dust in its kind of orbital vicinity. That process is called accretion. Differentiation, we just talked about. It's a denser material sinking to the bottom through the force of gravity. Okay? Now, another key part about the interior heating is radioactivity. There are lots and lots of radioactive elements. Radioactive elements do tend to be denser. Well, in fact, they definitely tend to be denser, okay? Not that, it's possible to have lighter materials, lighter elements that are radioactive, but basically all the denser ones in the periodic table are radioactive. And all those denser radioactive materials, they're going to be in the interior of the planet. They're going to be decaying, releasing energy, changing nuclear binding energy into heat. Okay, it is a very important source of heat, even today. Okay, inside of the planet, continually creating heat through radioactive decay. Okay, on a large scale. Okay, so that's where the heat came from. It came from things smashing together, that all that original energy of accretion, and then continued energy from radioactive decay. But it's not like that heat can just stay, right? The heat also cools, it dissipates, it flows off into space. Okay, so convection is one way that heat can flow in planetary interiors. It transports heat as hot material rising and cooler materials falling. This happens in the mantle of our planet. We have these big so-called convection cells. They're like giant boiling sections of rock, but moving at a very low scale, very low velocity, very large time scale. Okay? Conduction transfers heat from hot materials to cool materials. So conduction can be happening through the lithosphere. Heat is just passing through, right? Just conducting through the rock. If you heat up one side of a rock, the other side gradually gets warm as well. Okay, that's conduction. That's molecules kind of bouncing together within the solid materials. Okay, it doesn't require a liquid. It works with solids as well. Obviously, convection requires liquid. Okay, and finally, radiation, because ultimately we are losing energy, sends energy into space. Light leaves the planet energy leaves the planet as light, which is a form of heat. Okay, radiation is a form of heat flow. Now, we are getting more energy from the sun than we lose as light, through these processes of heat flow, but we are giving off some energy. We're glowing in the infrared due to our own interior heat. We're reflecting in the visible light spectrum due to reflected light from the sun. Okay? Okay. But size is so important for all of these processes. In fact, size is important for more than just interior heating and cooling, but it has a big role to play for interior heating and cooling. And what is that role? Well, smaller worlds cool off faster and harden earlier. The Moon and Mercury are great examples of small worlds that cooled off fast and became geologically dead. They don't have any molten core left. They're just completely cooled off. They've lost all of their interior heat, or nearly all of it. Okay? And that's because the smaller a world is, the greater its surface area to volume ratio. Okay? And here's the idea. The heat content depends on the volume. The loss of heat through radiation depends on the surface area. That should make sense, right? Bigger surface area, more area to radiate heat. The time to cool depends on the surface area divided by the volume. That's the ratio I spoke of. Okay? There it is. So the volume for a sphere, assuming a perfect sphere for planets, a good assumption, all right, is 4/3 pi r cubed. That's the volume of a sphere. Meanwhile, the surface area of a sphere, another geological, I said geological, I meant geometric formula, is 4 pi r squared. You don't have to memorize these, but they might look familiar. When you cancel out all the like terms, you end up with a 3/r relationship. This tells you that larger objects have a smaller ratio and cool more slowly. All right? So that means if you double the radius, then your rate of cooling is 1/2. Okay? You cool off 1/2 as fast. Okay? Well, times 3, right? Because you do have that 3 value as well. But the rough ratio is 1/r. Okay? So hopefully that makes sense, right? Smaller worlds cool off faster, and it all has to do with math. Okay? All right. So why do some planetary interiors create magnetic fields? Whoa, magnetic fields, right? We know we have one here on Earth because we have compasses, right? Compasses point towards magnetic north, okay? So not all worlds have magnetic fields. What are the ingredients necessary to have one, okay? Well, first of all, we have to understand a bit about the source of magnetic fields in general, all right? So magnetic fields are created by one process only, which is the motion of charged particles, okay? All magnetic fields are created by the motion of charged particles. You might wonder then, like, wait, I have a magnet on my fridge. I stick that magnet on there. That magnet's just like a little kind of plasticky, on one side, maybe sort of metal-looking surface on the other. Where are the charged particles in that? It's just a little inert, object, right? Well, they're at the atomic scale. The charged particles in the case of a refrigerator magnet are the actual electrons orbiting the atoms inside the material. But they're all lined up, so together they actually create a magnetic field. That's why not everything's magnetic, because a lot of times all those electrons are not lined up in a uniform way, but in magnets they are, man-made or natural, okay? So think magnetite, the rock. Okay, but you can also create a magnet by just running a current through a wire and wrapping that current in kind of a cylinder shape, shown like in this figure. In that case, the pink lines become the magnetic field that you've created with a battery and some wire. All right? Well, the world does the same thing, Earth, that is. A world can have a magnetic field if charged particles are moving inside. There are 3 key requirements, and these are quite fascinating. You have to have a molten core that consists of electrically conducting material, okay? So electrically conducting interior. And it's got to be molten, it's got to be liquid and moving around, all right? So you have to have this kind of this movement of rocks that have the ability to conduct electricity. So in this case, this would be the convection cells in the liquid outer core of our planet. Furthermore, you have to have convection, right? There has to be movement, because that has to kind of, that convection, that rubbing together of the molten rock, that creates all the free charge. So you need to have all that extra charge built up, okay? So you have to have a liquid, you have to have extra charge built up, and then the last ingredient is you have to have rotation. Because essentially, the liquid molten core with its convection, that's just doing the job of kind of like, that's like the battery, all right? So, but a battery itself doesn't create a magnetic field. If you look at the previous picture, you have to connect the battery and then twist it around. When you connect the battery and have it in this twisting fashion, what you're doing then is you're creating rotational motion, because you're running a current through that wire, and then that current is essentially spinning around and around, and the current keeps being regenerated thanks to the battery. Well, in Earth's case, the current is being regenerated from the rubbing together of the molten rock, but the spinning part comes from Earth's own rotation, and it has to be relatively fast. Ours is pretty fast. We make a full rotation about our own axis every 24 hours, okay? So that's it. You need fairly fast rotation, and you need to kind of charge up the interior with molten conducting material and convection, okay? So that's it. That's how you create a magnetic field. The Earth does a good job of it, all right? All right, so what have we learned so far? All terrestrial worlds have a core, mantle, and a crust, okay? They're not all the same relative size, but they all have it. The denser material is found deeper inside. That's differentiation. The interior heat drives geological activity. We'll talk about that more. Radioactive decay is currently the main heat source, but originally it would have been kind of from the very formation of the planet, the accretion, all that energy of rocks smashing together. All right, why do some planetary interiors create magnetic fields? Well, it requires motion of charged particles inside a planet, and it requires rotation of that planet. All right, so let's talk about the surface, not just the inside. All right, let's move on to a new topic. What processes shape planetary surfaces? How do impact craters reveal a surface's geological age? And why do the terrestrial planets have different geological histories? All right, here's the planets again. We'll kind of keep coming back to these. And the moon, odd one out. All right, so processes that shape the surface. Well, we can kind of summarize all the things that would, if you look at a surface and you take a picture of it and you see all these different surface features, where do those surface features come from? Well, impact cratering, that's a big one. All right, asteroids or comets crashing into the surface of a world. Now, is that a big one on Earth? Not so much, but we'll talk about why. Volcanism, all right, eruption of molten rock into the surface, big old volcanoes. They have them on Mars. There's volcanoes on Venus. We have them here on Earth, right? I mean, you wouldn't have the Hawaiian Islands without volcanism. Tectonics, the disruption of a planetary surface by internal stresses. So the very surface of the planet cracking and moving around. And erosion. Surfaces changed by wind, water, or ice. All right, so that's weather and glaciation. That would cause erosion. Okay, all right. So let's cover each of them. Impact cratering. So most cratering happens soon after the solar system formed. Okay, that's actually a key part of our solar system history. Okay, and it's going to be a key part of us understanding terrestrial worlds. Actually, doesn't really help so much understanding of Jovian worlds, but we're not talking about Jovian worlds, are we? All right, and the reason it's so important is because it's going to allow us to kind of age planets, at least kind of talk about maybe how geologically active they've been. But first of all, why should we even assume that most of the cratering happened early in the solar system? That's because early in the solar system, there's still a lot of leftover pieces from the accretion process, right? And then over time, they either got flung to the outer edges of the system and become the Kuiper belt and the Oort cloud, or they kind of got trapped in an eternal dance with Jupiter and became the asteroid belt, or they crashed into planets and that was it. They became part of planets. But in those first few 100 million years, there was still a lot of leftover asteroids and comets. Okay, so that was the period of bombardment. We'll talk about it more. Okay, so craters are about 10 times wider than the object that made them, right? So there's a big difference, right? A small asteroid makes a very large crater, right? A lot of energy is being released. And small craters greatly outnumber large ones, all right? That makes sense. A lot of smaller pieces of space junk crashing into planetary surfaces. All right, here's some examples of impact craters on the moon and Earth, right? Pretty cool. All right, here are some impact craters on Mars. All right, here's a standard crater, nice size there. Here's an impact crater on icy ground where we see some muddy behavior. All right, and here we actually see a impact crater that was eroded, right? Clear cases of erosion. All right, so it looks like it would have happened from rainfall. So maybe there was rain billions of years ago on Mars. Okay. All right, volcanism. So volcanism happens when molten rock magma finds a path through the lithosphere. Okay, that's that light outer core of the planet, breaks through and starts to bubble up, eventually kind of like sealing off the very crack that allowed it to go through, but for a while bubbling up to the surface. Molten rock is called lava after it reaches the surface, magma when it's under the surface. All right, so talk a little bit about lava and volcanoes. The thickest lava makes steep volcanoes, which are called stratovolcanoes. Slightly runnier lava makes broad shield volcanoes, like the biggest volcano in the solar system called Olympus Mons on Mars, which is a huge shield volcano. And runnier lava still doesn't make any really volcanoes, but just makes big lava flats, all right, also called lava plains, all right. The Maria on the moon are an example of very runny lava making huge lava plains. Wait, lava on the moon? Are there volcanoes on the moon? Not anymore, but there used to be, okay? All right. Outgassing is very similar to volcanic behavior. Volcanism also releases gases from the Earth's interior into the atmosphere, and that can have important consequences chemically and greenhouse gas-wise in terms of the atmosphere. All right, so now tectonics, next on the list. So convection of the mantle, these are those big, rising of hot mantles, sinking of cooler sections of mantle. Convection also occurs in a boiling pot of water. Convection also occurs in atmospheres, okay? It just requires a fluid. So convection of the mantle creates stresses in the crust called tectonic forces. Compression of the crust creates mountain ranges. Valleys can form where the crust is pulled apart. Okay, that's plate tectonics. Okay, maybe you've seen it in geology class. Maybe you haven't, that's fine too. But if it sounds familiar, that's good. All right? Okay. So Earth's continents slide around on separate plates of crust, right? Earth has really remarkable plate tectonics. We'll talk about the fact that no other planet in our solar system does. Okay, maybe that's fascinating, right? We're the only of the terrestrial worlds that actually has these really defined current ongoing plate tectonics. All right, and we have these plates, with interesting names like the, maybe the Eurasian plate and so on. And they move around, crashing into each other. Here the faults are labeled like the San Andreas Fault, which are the dividing lines between plates. But they're constantly moving, sliding on top of each other, sliding under each other, crashing in and pushing each other up, and so on. Erosion, right? Another factor that shapes the surface of worlds. Erosion is a blanket term for weather-driven processes that break down or transport material. Okay? It can include glaciers, rivers, and wind. All right? Okay? So let's sum up each. Erosion by water, all right? Erosion by water. So the Colorado River continues to carve out the Grand Canyon. It's an ongoing process, but it took a long time to get as deep as it is today. Okay, so the water just carries away materials. Some materials are easy to be carried away than others, right? Density and properties of the rock have a big factor there. Glaciation carved out Yosemite Valley. So glaciation is incredibly powerful but slow moving. And then lastly, we've got wind. Wind wears away rock and builds up sand dunes, okay? So wind is most effective on rock that's already been broken up into small pieces. That's why it's so pronounced on sand. And you don't see, like wind lines on like solid basalt cliffs, right? All right? And then we can have other types of erosion. Erosion can create new features such as deltas by depositing debris somewhere else. Okay, so now I mentioned this idea of bombardment. Let's get back to it. How do impact craters reveal a surface's geological age? Well, most cratering happened in the first billion years, okay? And that's kind of a broad statement. You can even round it to the first 500 million, but the time isn't precisely known. But definitely of the 4.5 billion years of the solar system, it was in that, somewhere in that first half to 1 billion years. A surface with many craters has not changed much in 3 billion years. So when we look at worlds that have lots of craters on their surface, we can figure that most of those craters came over 3 billion years ago. And since they're all left, that means that that world hasn't changed much in those 3 billion years, right? There's very few major collisions going on. There's very few major comets and asteroids crashing. And you might be like, oh, you hear about them. You hear about flybys. You hear about comets. You hear about sighting comets and asteroid flybys and so on. But those are so rare compared to what they were like billions of years ago. All right. So the moon, for example, some areas of the moon are more heavily cratered than others. The younger regions were flooded by lava after most of the cratering occurred. So the big flat regions, the maria, these big lava plains, there are some craters on top of the maria. Here's one right here, but mostly there's not, because that means the maria occurred at some point, maybe 3 billion years ago. And when those big slow lava with a very low viscosity lava kind of spread out over the moon's surface, bombardment had ended, and so those lava plains hardly got covered up. All right, so the cratering map of the moon's entire surface, and we can see, right, big lava plains with only a few craters on them, whereas the older parts that weren't covered with lava are covered in giant craters, almost touching each other. All right, this is ancient moon here, and this is newer moon surface. Okay, now the newer moon surface can still be about 3 billion years old, because the important thing to remember is that once that bombardment phase was over, it was over. All right, and the rate of comet and asteroid collision had just fallen off precipitously. Okay, so why do the terrestrial planets have different geological histories? Because we'll see, again and again, through this video and the next, that they have very distinct histories. Well, the size, right? We mentioned this. The smaller worlds cool off faster and harden earlier. That's going to have a big effect on the surface, on the whole features of the planet. The larger worlds remain warm inside, promoting volcanism and tectonics. Okay, so we should definitely expect Venus, Earth, lots of tectonics and volcanism, and Mars to a lesser degree. The larger worlds also have more erosion because gravity retains an atmosphere. Okay, so that's the thing, right? If you're too small, there's not enough gravity to actually hold on to gases to get an atmosphere. Okay, what about distance from the sun? Well, that matters too. Okay, absolutely does. Planets close to the sun are too hot for rain, snow, or ice, and so have less erosion. All right, planets close to the sun basically are so hot that they can't hold onto an atmosphere because the atmosphere is too energetic to stick around, even if they were large. Okay, of course, Mercury is small and close to the sun, so there's no chance to have an atmosphere. The hot planets have more difficulty retaining an atmosphere, right? Because the very fast gases tend to achieve the escape velocity of the planet and just take off, never to return. The planets far from the sun are too cold for rain, limiting erosion, right? So that's kind of the case of Mars, right? It's so cold that the atmosphere isn't as energetic, okay? Especially, without greenhouse gas effects. Planets with liquid water have the most erosion, all right? And that's ours. So what about Venus? Shouldn't Venus have liquid water? Well, more on that later, okay? Turns out Venus, special things are happening on Venus, okay? But that makes sense because there should or could make sense because there's all these complicated factors and it's not like one factor dominates. You have to take all the pieces of the puzzle together, all right? And rotation, okay? Which actually ends up being a big part of the piece of the puzzle for Venus, okay? Planets with slower rotation have less weather, less erosion, and a weak magnetic field. Remember, right? Because you need relatively fast rotation to maintain that magnetic field. So very slow rotating planets should have a very different feature than fast rotating planets like Earth. Planets with fast rotation have more weather, more erosion, and a stronger magnetic field. All right, neat. Okay, so thought question. How does the cooling of planets and potatoes vary with size? Okay, should be able to answer this one. Okay, all of the above. All of the above, that is. All right, they all make sense. They all match up. Okay, ratio, larger size, takes longer to cool. Yep, it all matches. Okay, so what have we learned? Cratering, volcanism, tectonics, and erosion. Those are the big four that shape surfaces. All right, how do impact craters reveal a surface's geological age? Well, it's all about that, that first billion years is when most cratering happened. If you don't see a lot of cratering, then that surface was formed after the first billion years. Simple as that. Why do the terrestrial planets have different geological histories? The differences arise because of the planetary size, distance from sun, and rotation rate, okay? So those are kind of some big factors. And there's a lot we can kind of unpack about those factors, but that's a good starting point, all right? So let's talk more specifically about atmospheres, okay? So atmospheric basics. What is an atmosphere? How does the greenhouse effect warm a planet? And why do atmospheric properties vary with altitude? All right? So an atmosphere is a layer of gas that surrounds the world. Okay, we have one. Ours has a lot of nitrogen and oxygen. We can breathe our atmosphere, and it is incredibly important for life on Earth. Okay? So Earth's atmosphere is about 10 kilometers thick. It consists mostly of molecular nitrogen and oxygen. So N2 and O2. Okay? So what's the deal with atmospheric pressure? All right? Well, atmospheric pressure has to deal with temperature. You heat something up and it becomes bigger because the molecules bounce around more, right? Exerting more pressure on whatever contains those molecules. That's the example here with a balloon, okay? So another way to think about pressure is we can think about stacking gases on top of each other. So pressure and density decrease with altitude because the weight of the overlaying layer is less. All right, Earth's pressure at sea level is 1.03 kilograms per square meter, or 14.7 pounds per square inch, which is called 1 bar, if you've seen that unit of atmospheric pressure. But as we go up, up, up into the atmosphere, that pressure falls off. Kind of like if you imagine a stack of pillows, the pillows at the bottom would be more squished than the pillows at the top. Same idea, the molecules are more squished at the bottom of the atmosphere. All right? So there's no clear upper boundary to Earth's atmosphere. It just becomes progressively thinner and thinner. Most of Earth's gas is less than 10 kilometers from the surface, but a small fraction extends to more than 100 kilometers. Altitudes more than 100 kilometers are considered space. Okay, so 10 kilometers is kind of the breathing part. That's the atmosphere that we can think of as in a biological sense. In terms of like aerodynamics, you know, maintaining a lift in a plane, you can get up to 40, 50, 60 kilometers. And then in terms of having a spacecraft, like a satellite or an international space station, you want it well above 100 kilometers because you want it where there's really no molecules left for tiny little collisions that would eventually slow that spacecraft or satellite down. Okay? All right. So small amounts of gas are present even above 300 kilometers, right? So that means that the International Space Station is within, you know, a tiny, tiny area where there are still some leftover molecules, okay? All right. So what are the effects of atmosphere? They create pressure that determines whether liquid water can exist on a surface, okay? So atmospheric pressure is a big deal, all right? Because otherwise the vacuum state of space, that very low pressure that defines outer space, means that water would boil at very low temperature and it'd be very hard to maintain liquid water. It would just turn into a gas, okay? They can absorb and scatter light, okay? That's why we have a blue sky and red sunsets. It's all about the absorption and scattering of light. They create wind, weather, and climate, okay? Which can have huge effects on kind of like just maintaining a stable environment for life again, right? Kind of keep coming back to this way that atmosphere, it's hard to think of atmosphere and nurturing life on Earth, okay? Atmospheres interact with the solar wind to create a magnetosphere. Essentially, that's the idea that's where you get the aurora borealis or the northern lights from. All right, and it also protects us from harmful, very high energy charged particles that are coming from the sun. That certainly would disrupt modern society because we need to have electricity on a large scale. And they can make planetary surfaces warmer through the greenhouse effect. Okay, so there's a list, right? It's a fairly complicated list, but that really does a good job of summarizing what atmospheres do. Okay. So, how does a greenhouse effect warm a planet? Well, let's think about it, okay? So, the greenhouse effect works like this. Visible light passes through the atmosphere and warms a planet's surface. So this would be light coming from the sun, okay? Lots of visible light in the rainbow of visible light, so Roy G. Biv, red, orange, yellow, green, blue, indigo, violet light, okay? Also a little bit of ultraviolet, but some of that is getting absorbed before it makes it to the surface. Some infrared, right, coming to the surface, but that's a lot of light energy coming down, okay? Some of that light energy, maybe gets captured by, photocells in plants, or, just gets absorbed somehow, right? Gets turned into the molecular motion of the oceans. But a lot of that light just gets reflected right off the surface, okay? Just comes down and bounces right back off, right? Because there's just tons of reflection, snow, right? But actually everything reflects. If I see something that has the color red, that's because it's reflecting red light, okay? So lots and lots of, red roses, right? They're reflecting red light. So lots of reflection occurring, right? So now we got, this rainbow of light coming back up, shown as yellow because it's kind of supposed to represent the middle of the visible spectrum, okay? So coming back up off the surface. But here's the thing. That yellow light maybe can go back up into space, right? Get reflected right away. That's why our planet is visible if you're out in space, okay? Visible from the moon, for example. You can see all the colors of Earth. But some light actually never makes it back into space, in particular infrared, all right? The atmosphere absorbs infrared light from the surface, trapping it inside, okay? So essentially, you can think of the atmosphere as being opaque to infrared light, all right? It won't let it pass through, all right? So that's interesting because that means that infrared light wouldn't have come from the sun much either. But that's fine, right? Maybe that light just got rejected from the sun. But the surface created infrared light. How does the surface create infrared light? Because I said that this is reflected light here. Okay? Reflect. But this is actually created. That's because of something called black body radiation. Essentially, the molecules are vibrating. All these molecules are vibrating and they create light. And that's the same sort of light that you would see of heat goggles, right? Kind of heat sense or a heat sensing camera. All that is heat. It's low energy heat, but it is heat. And in its entire surface of a planet, it adds up. And all that infrared heat, invisible to our eyes, but detectable with devices, that can't pass through the atmosphere. It's trapped. And that's actually the same phenomenon of glass. So think about a car, right? A car left in the sun on a cold winter day is going to be really warm inside. And that's because all the visible light that passed through the glass, the glass being transparent to visible light, well, that visible light warmed up the seat, warmed up the dashboard, and that all the molecules in the seat and the dashboard started vibrating, creating their own light in the invisible infrared. Well, that light hit the glass, and it turned out the glass was opaque, would not let the infrared light pass through, just due to its own molecular properties. And that means all the infrared light was forced to bounce around inside the car, warming up all the air molecules, creating all that motion, that kinetic energy, that warm air. Well, that's exactly what's happening inside the Earth's atmosphere. Same process, but on a much larger scale. Okay, and some different details, right? But the same general idea. Okay, I think it's really cool. So, a planet's surface temperature is determined by the balance between the energy from sunlight it absorbs and the energy of outgoing thermal radiation. Okay, like that outgoing, infrared radiation. Okay. So a planet's distance from the sun determines the total amount of incoming sunlight, that is. It's very important, okay? A planet's rotation rate affects the temperature difference between night and day, okay? So if you have a really slow rotation, then your night side can cool down dramatically while your day side heats up dramatically, okay? So that can have a big effect, okay? Reflectivity. So a planet's reflectivity, also called its albedo, is the fraction of incoming sunlight it reflects. So the moon, for example, has a very high albedo because of its kind of the particular type of dust that covers most of its surface. Very reflective. Earth would be less, right? We have a lot of materials that aren't as reflective as, kind of white dust. All right? Planets with a low albedo absorb more sunlight, leading to hotter temperatures. And that's true of Earth compared to the moon. Okay? All right. So let's think about no greenhouse temperatures in this very interesting table. Okay. So first of all, we have our worlds here. We have our distance from the sun in this column, all right, measured in astronomical units, so Earth is exactly 1. The moon, on average, is also exactly 1, on average. Here we have the albedo, or reflectivity, okay? Mercury, fairly reflective. Venus, very reflective. Earth, moderately reflective, all right? The moon, actually kind of moderately reflective. And then Mars, okay? So the Earth's reflectivity, that actually surprises me. I thought it was lower than that. Okay, but I guess we have cases of surfaces that are more reflective. And then we have the no greenhouse average surface temperature. Okay, so this would be without an atmosphere. So Mercury would be very hot without an atmosphere because it's close to the sun. Okay, but as soon as we get away from Mercury, the temperature falls off quite a bit. Okay, Venus would be -40. Okay, Earth would be negative 16. The moon would be -2, and Mars would be -56. It's so far away from the sun. All right, and these temperatures are based also on the rotation, okay? All right, and then we get to the actual average surface temperature, okay? Well, we see that Mercury is quite different, and that's because it's so slow, it's able to heat up very dramatically during the day and cool off quite a bit at night, okay? So instead of being an average of 163, it's kind of extremes on either end of that, all right? Venus, for some reason, is really, really hot, okay? Now that's because it has an incredibly dense atmosphere. We'll talk more about Venus. It's a very special case. Earth is definitely hotter than it's negative 16. Thank goodness, right? That would be a very cold planet, okay? And then we've got the moon, okay? The moon also has very hot temperatures and very cool temperatures, again, because of its slow rotation rate, okay? And then we've got Mars, which actually is about exactly as cool as we would expect it, because it doesn't have much greenhouse because it has a very thin atmosphere. So then we see that the effects of atmosphere make Venus 510 degrees hotter than it would be without an atmosphere, makes us 31 degrees hotter than we would be without an atmosphere, and makes Mars just moderately 6 degrees hotter than it would be without an atmosphere. Still makes Mars very, very cold, again, because it's relatively far from the sun. So we see that atmospheres can be great if you get them just right, right? The heating of our atmosphere is crucial. We want a greenhouse effect. But look what happened in Venus. Venus, and we'll talk about this later, is sometimes called a runaway greenhouse effect because it's way too hot. Okay, that's what you don't want from atmosphere. You don't want it to heat up the planet to uncontrollable temperatures. Okay? All right, so what would happen to Earth's temperature if Earth were more reflective? Okay, it would go down because we would be losing energy. Being more reflective would make us cooler. Okay, if Earth didn't have an atmosphere, what would happen to its temperature? Okay, think about it. Okay, less, more. Yep, it would go down a lot, more than 10 degrees Celsius. If we lost our atmosphere, we would be, as you saw on the table, about 30 degrees cooler in Celsius. Okay, so let's talk about some properties of the atmosphere, the actual dividing lines. Okay, so what are the properties of the atmosphere that vary with altitude? So this is quite interesting. Okay, so first, light's effect on the atmosphere. All right, so there's a few things that can happen. We can have ionization, which is removal of an electron, and that can happen due to incoming energy. X-rays, for example, have enough energy to ionize the atoms in the atmosphere, which is a high energy process, just knocking an electron off. We can also have dissociation, which is destruction of a molecule. This is also a fairly high energy process, but less high energy. It happens from ultraviolet. And a good thing here is that we should think of X-rays as higher energy than ultraviolet, and that's kind of the rule of thumb. And that's the idea, is that with the highest energy light is X-rays, the lowest energy light is going to be like radio waves, okay? Then we have visible light. Visible light primarily does something called scattering, which changes the photon's direction. A photon is a name for a particle of light. Wave is both a particle and a wave. That's a story for physics class. We won't get into the details here. And then finally we have absorption. So here we have the lowest energy light, infrared, is so low energy that it can match the vibrational energy of molecules, and some of that energy just hits a molecule and just causes it to start spinning, and just the light is completely absorbed into the rotational kinetic energy of the molecule. Okay? So these are kind of going from highest energy at the top down to lowest energy at the bottom. These are kind of common processes that are happening. Okay? Great for physics class. They're super fascinating, but maybe a little tangential for this class. Okay, so just summarizing the information here, right? I already said it all, so I'll kind of move through it. So let's talk about the different parts of the atmosphere. Okay, so we're going to start from the bottom up. So the very bottom is the troposphere. This is the lowest layer of Earth's atmosphere. It's the 10 kilometers. It's the part of atmosphere that supports life. Less so, right, when you get up to the top of Mount Everest, but still kind of supporting life. Okay, temperature drops with altitude. It is warmed by infrared light from the surface and convection. So all the warmth in this dense, because this is by far the densest part of the atmosphere, all the energy here is actually coming up from the surface, okay, and then kind of moving around through convection, kind of moving around through these big, wind processes, high pressure, low pressure regions that are, kind of air pushing up and falling down and so on, okay? So that's what's happening. Now, I do want to stress that idea of high pressure, because pressure, due to the combined effects of stacked molecules on top of the lower atmosphere and the gravitational pull on those molecules, the consequence of that is that pressure falls off exponentially, which is to say really fast. So as you go up into the atmosphere, the pressure doesn't fall off, you don't get half the pressure when you double your altitude. You get a really big decrease in pressure, okay? So kind of good reality check there. As we go and we talk about these other parts of the atmosphere, we should expect the pressure to be less than 1% what it is down in the breathable parts, below the peaks of the highest mountains. Okay? All right, so moving on. The stratosphere. Okay, so this is the layer above the troposphere. Nothing lives up here. All right. The temperature rises with the altitude in the lower part and drops with the altitude in the upper part. It's warmed by the absorption of ultraviolet sunlight. Okay? So at first, as you go up, the temperature is actually increasing because you're going up into a region where there's more and more ultraviolet light coming in. But then as you move up higher and higher, what happens is the energy starts falling off because there's less molecules to actually cause that temperature to be propagated in the first place. Okay, and when I say that, I also I'm going to give a caveat about temperature in a second. But for now, let's kind of just remember this rule about the stratosphere. Okay, rises with altitude in the lower part, and then drops with altitude in the upper part. Okay, and let's see. I'm trying to remember if this one has a temperature scale. Yeah, so it's this red line here. Okay, so the red line here was just the gradual falling of the temperature, right? Getting very cold at the peak of Mount Everest, right? negative 50 degrees Celsius, and then we have a bit of a rise. Okay, and there's a weather balloon. That's the highest weather balloons go, right? And we have a bit of a rise, peaks out there, right? So you can actually find a part of the stratosphere that is about 0 degrees, right? Cold but not unbearably cold. But then it really starts falling off again, getting even colder. Okay. So, but again, a caveat I'm going to say in a minute about temperature, because right now you're probably thinking, oh, temperature, what? You're like, oh wow, you could go up to 50 degrees above the surface of Earth, and it could just be 0 degrees Celsius. I mean, 0 degrees Celsius, you just need a jacket, right? Well, not quite. I'll tell you why. Okay. So now we get into the thermosphere. Now the thermosphere is really hot. That's weird. Layers at about 100 kilometers altitude, the temperature rises with altitude, just steadily rises the whole time. That's because now we've got into a region where the input of energy is primarily caused by X-rays. That's high energy light and more ultraviolet, okay? And so here we have, ionization of gases, right? We have a lot of high energy light coming in. And all that, the thermal radiation has no effect on the thermosphere, okay? But it's called the thermosphere because it's so hot, okay? Notice the temperature, right, shoots up, and by the time you get to the edge of the thermosphere, you're talking about a temperature, above 0 degrees Celsius, okay? And then finally, we have the exosphere, the highest layer in which the atmosphere gradually fades. Right here, this is above 100 kilometers, all right, fades in space. Temperature rises with altitude. The atoms can escape into space now, right? This is where we actually lose atoms. Atoms that make their way up into the exosphere might never come back down, okay? They can just get lost to space, all right? And is also warmed by X-rays and UV light, just like the thermosphere. Okay, but here's the thing, right? Because look at this, right? If you go up in the exosphere, you could have temperatures that are 100 degrees, even 1,000 degrees Celsius. Oh my gosh, do you burn up? Is that why when satellites come back down, from orbit, is that why they burn up? Because they're passing the exosphere? No, that's actually not why they're burning up. They actually start, the big flames that cover them are much, much further down, really when they're passing into the stratosphere. It's when they reach the regions where there's higher density, a higher concentration of molecules per cubic meter. No. The high temperature here doesn't mean high heat, okay? Instead, this means that there's a few molecules, just a few molecules per cubic centimeter that are incredibly energetic, because they've absorbed a lot of energy from those X-rays, okay? But that doesn't mean that you would feel warm there. Because, you could have, 1,000 molecules that are moving 10,000 meters per second, and you wouldn't feel warm from them, because that's just 1,000 molecules. That'd be imperceptible, to the trillions upon trillions of molecules that make up the surface of your skin. No, you wouldn't actually feel that heat. It'd be totally, even though they're going so fast, you wouldn't perceive them. You wouldn't feel warm. If you tried to go out into these high temperatures, you wouldn't feel heat. You'd freeze, okay? So high temperature does not mean high heat. You have to have a lot of molecules, so high density and relatively high temperature, in order to have high heat. And that is only actually possible in the troposphere. Okay, so now a bit more about the atmosphere and light coming in, okay? Why is the sky blue? Right? It's a good question. Kids ask it all the time. It's because of scattering, one of those processes. Okay, that's the third or the second least energetic of the processes of light. Right, it's the third most energetic process of incoming light from the sun. Okay, So, sky is blue. Well, the atmosphere scatters blue light from the sun, making it appear to come from different directions. So that would be like an observer at noon in Hawaii, they'd see blue light, okay? But then at that same point in Florida, it's sunset, and that observer in Florida is going to see a red sunset because all the blue light got scattered to observers along the way, so only the red light makes it to the observer that is looking at light at sunset, okay? So that means that the same explanation for why the sky is blue is why sunsets are red. It's the scattering of blue light, okay? It just has to do with your direction to observing that light. I think this figure does a good job of showing that, okay? So Earth is the only planet with a stratosphere because of the UV absorbing ozone molecules. Okay, so that's a crucial thing about the stratosphere. That stratosphere where went up and then went back down. That is very unique to one particular type of molecule we have, O3. Okay, those same molecules protect us from the sun's UV light. Okay, and we can see the stratosphere behavior, that little stratosphere peak, doesn't exist on Mars and it doesn't exist on Venus. The curves are different between Mars and Venus, so there's other stories to be told. But the one thing they have in common is they don't have a stratosphere with ozone. Okay, so good difference there. Okay, and the ozone isn't the only part of the greenhouse, right? But it is probably the most important greenhouse gas. So if you really want a quick kind of thing to think of, if you think of greenhouse effect, think of ozone. All right. So we mentioned the magnetosphere a little bit when we talked about magnetic fields. Let's get more into it because we're talking about details of atmospheres. Okay, so the magnetic field of Earth's atmosphere protects us from charged particles streaming from the sun, the solar wind. How does it do it? Well, it redirects those particles because the magnetic field affects those charged particles' trajectories. Okay, they experience a force due to the magnetic field because they're charged. Okay, non-charged particles wouldn't experience a force from a magnetic field, by the way. Okay, all right. The charged particles from the solar wind energize the upper atmosphere near the poles. Okay, because the poles are where the magnetic field lines really aren't parallel to the surface, and that allows charged particles to follow the field lines kind of down to the poles, north and south. And that's why we have the auroras, all right? The northern and southern lights. All right, so what is the atmosphere? Well, it's a layer of gas that surrounds a world, right? You need a fair amount of gravity, a lot of size in order to have one. We talked about that. Small worlds can't trap atmospheres. How does a greenhouse effect warm a planet? The atmospheric molecules allow visible sunlight in, but traps infrared light, okay? Why does atmospheric property vary with altitude? Well, it depends on how the atmospheric gases interact with sunlight at different altitudes, right? And we talked about the 4 ways they interact. All right, so let's talk a little bit about weather and climate. What creates wind and weather? What factors can cause long-term climate change? And how does a planet gain or lose atmospheric gases? All right, so here's a little bit about weather and kind of the main winds that would exist on a planet like Earth. So weather is the ever-varying combination of wind, clouds, temperature, and pressure. Local complexity of weather makes it difficult to predict. On the other hand, climate is the long-term average of weather. Long-term stability of climate depends on global conditions and is much more predictable. Global winds blow in distinct patterns. Equatorial is east to west, mid-latitudes west to east, and finally the high latitudes back to east to west, just like the equatorial. So we have bands of weather, okay? Why is that? That's due to convection cells. Right, we have these big convection cells due to our cold poles, right, which are a testament to our axial tilt, and then combine that with our rotation, and you've got yourself these convection cells. Okay, without rotation, there'd just be 2 large circular cells rather than the 4 than these donut-shaped shells here. Okay, and now the Coriolis effect. I'm just going to move through this quickly, but the Coriolis effect essentially is the idea that as you move away from the axis of rotation, your motion gets bent to one direction. And it gets bent in one direction if you're moving away from the axis of rotation. And then there's a different bend as you're moving the other way. That's why we have rotation in the southern hemisphere in one direction and rotation in the northern hemisphere in the opposite direction. It's all due to the Coriolis effect, which can be explained with this analogy of someone on a large turntable rolling a ball. Okay, and the ball would take this path. Okay, and to quickly summarize it, if the turntable is at rest, the ball would go straight. But since the turntable is not at rest, its apparent motion is in that direction. Okay, it has to do with conservation of momentum, and this creates these rotations. Okay, it creates a clockwise rotation in the southern hemisphere and a counterclockwise rotation in the northern hemisphere, both caused by the same effect, angular momentum, called the Coriolis effect. Okay. So the conservation of angular momentum causes the large storms to swirl. The direction of the circular depends on the hemisphere, as I said. Okay? All right. So the Coriolis effect deflects the north-south winds into east-west winds. All right, and here we have the picture of all the bands. Okay. So instead of just having the two big donut shapes, we have 1, 2, 3, 4, 5, 6 of them. Okay, we have the 6 bands that define Earth's weather. All right. So here they are. Right, shown again, kind of in the 3D view, and then the kind of this 2D directional view. All right, so 3D, 2D. All right. So let's talk a little about kind of the precipitation cycle. Right, water evaporates, goes into clouds, falls back down, and then flows back to be evaporated again. All right, so what factors can cause long-term climate change? All right, so here are a few. Right, solar brightening, as the sun brightens. Right, this takes billions of years. That would increase the amount of sunlight coming to the planet, which would warm the planet. Changes in reflectivity. So if either the atmospheric properties or the surface properties of a planet change, that can change the reflectivity. That could certainly change the climate. All right. A change in axial tilt. All right. So greater tilt makes more extreme seasons, while smaller tilt keeps polar regions colder. What could change axial tilt? Well, a large collision, although that would also change Earth, dramatically as well, right? But perhaps like a gravitational flyby, right? So a close encounter with a large object could also significantly change the tilt, and also a change in greenhouse gas abundance, right? And this one, of course, is most relevant to our human condition, right? Our lifespans. All right. So solar brightening, summer rising up, axial tilt, already talked about it. All right. So small gravitational tugs do change the tilt, right? So like tugs from Jupiter, for example, over millions of years can change that, right? Currently we're at 23.5, but over time our degree has been as little as 22 and as much as 25 if we kind of look at the record of Earth's climate. All right, here's the reflectivity, and of course the greenhouse gases. All right, so how does the planet gain or lose atmospheric gases? Well, it can happen through outgassing, like volcanoes, right? So volcanoes can definitely release different gases that weren't already in the atmosphere, and they can do it on a large scale. It's happened. We definitely see that in the fossil record. Mass extinctions have occurred in the past due to outgassing here on Earth. We see it happening on other planets as well. Evaporation of surface liquid, right? So you kind of have a runaway effect. The temperatures start changing, causing more evaporation. Well, now those that evaporated water then changes the temperature more, which evaporates even more water, and so on. All right, and then you can also actually have impacts, right? If there's enough impacts occurring, that can significantly release gases that weren't there before. That wouldn't be so relevant now, but certainly would have been relevant back, billions of years ago during that age of bombardment, during the first billion years of the solar system. All right. We can also have loss of gases. So thermal escape of atoms, right? They can escape into space. They can be swept away by the solar wind if the magnetic field isn't strong enough. All right. They can condense on the surface, thus leaving the atmosphere and just kind of becoming a solid. All right. Chemical reactions with the surface can bind them to other molecules, also effectively taking them out of the atmosphere. And then large impacts blasting gas into space. Okay. So that's basically a way to give a big amount of energy to a few gas molecules, giving them escape velocity from that planet or world. Okay. So thermal escape has this formula right here. All right. So this is the velocity necessary for a molecule to escape. All right. K is a constant, T is the temperature that molecule is at, and M is the mass. So this tells us that lower mass molecules are going to have higher thermal velocities, and thus they're going to be able to escape more easily. Okay, and then we can see that a very small fraction actually achieve a high enough velocity to escape. Okay, but that tail, that small proportion, does mean that over time some do escape. So you don't need all of them to escape, you just need a gradual escape. So that means that over 100 millions of years, if few molecules are escaping, then they will continue to do so until there are none left. Okay? So summary here, what causes wind and weather? Atmospheric heating and the Coriolis effect. What factors can cause long-term climate change? Brightening, axial tilt, reflectivity, and changes in gases. And the changes in the gases have quite a few of their own sources, as we saw. All right? So we've learned that outgassing, evaporation, sublimation, that's them turning to solids, and impacts by particles and photons can all cause a gain of a gas. Actually, sublimation is a solid turning to a gas, excuse me. Losses are condensation, that's the gas turning to a solid. Chemical reactions, blasting by large impacts, sweeping by solar winds, and thermal escape. Okay. All right. So that summarizes finishes, I should say, the first video. I know it was a lot of information, but now I hope you can stay tuned or be on the lookout for the second video. We're going to get into some specific and interesting stories about the 5 worlds that we're discussing, the 4 terrestrial planets and our own moon. All right, well, thank you so much for watching this video.